Daniel, welcome in. You are a neuroengineer and the founder of Eightsix Science. You have recently raised money from Team Draper, which is one of the most important VC in the world. So welcome in and thanks a lot for joining me.
Yes, thank you for having me.
So let's start from the basics, which is on your LinkedIn bio, you have written Biohybrid brain replacement and whole brain explantation. Can you give a breakdown of what these two terms mean?
Yes, so these terms are names for two work streams that we have at the company Eightsix Science. As important context, the company tries to solve death or dying as engineering challenge by focusing on the brain through neuroengineering. So what that means is the biohybrid brain replacement means that we try to keep the brain running for as long as possible. So currently, if you're aging, your brain is slowly dying in a sense that entropy increases. You get faulty behavior, faulty mechanisms, and at some point it will die. Either way, there's no way around it. Even if your body is extremely healthy, your brain will also die at some point. You will get dementia, neurodegenerative diseases, and at some point you will eventually die. So one quest next to bioengineering, which is the approach to let's give you a magic pill that will reverse age your brain. Our approach is saying, okay, let's try to replace it actually, as we do with, for example, other organs like the heart. If you right now have like a malfunctioning heart, we replace it, be it with artificial pump or be it with a donor, like a donation, right? But the problem is with the brain, you cannot do that. You cannot just take your brain out and then put a new one in because that's not you anymore, because you are your brain. So how would you do that? You would try to gradually replace small pieces of your brain over time in order to have like this Ship of Theseus kind of mechanism. So the idea is whatever you are and stored in what we call like, or not we, just like the neuroscience community, engrams, which is like the physical representation of memory in the brain. We try to shift them around in the tissue, take the tissue out, it does not hold any memory anymore, and then insert, like surgically insert biological new tissue into the brain. And we do that over time. So whatever you are shifts around in the substrate, but at the same time, you basically rejuvenate the entire brain, which is awesome. And the biohybrid part there is quite interesting because since we engineer these brain tissues in the laboratory, we have an amazing engineering opportunity to mix them with small electronics. Why would we do that? There's actually one big reason. In order to functionally integrate them into your host brain, you need to stimulate the new tissue in the host brain so that they actually integrate in a better way into the host brain itself. And the second reason is the goal is to have an ultra high bandwidth brain computer interface at the same time. So you need to imagine it's like an inverse Neuralink in that sense. We instead of inserting a bunch of electrodes, like small needles to record and stimulate the brain tissue, we take the electrodes and print brain around it and then surgically implant that piecewise over time. So after a while, you end up with a young, healthy, rejuvenated brain that has at the same time an ultra high bandwidth BCI. So you can read and write into that brain. So that's like part one, right? And the second term that you mentioned, like functional whole brain explantation, which is if you have a biohybridized brain, as we call it, you can still die because even though you have like a young, healthy brain, or even you have a young, healthy body, like Brian Johnson, for example, you might still get hit by a bus or somebody, I don't know. I usually always give like the example of somebody stabs you in the face because it's like so visual. It's so easy that this happens, right? It's like the chance of dying is still here, even though we have the engineering mechanisms to basically degrade or make it statistically very unlikely to ever die due to aging or disease. So what's the best way to do that? We need to protect the brain. So the best way to do that is actually take it out and put it into a safe environment and let your brain control either a robot or in our case, initial case, a virtual body remotely. Because if the virtual, like your embodiment where you act agency onto the real world, if that gets destroyed due to like a disaster or whatever happens, you're still fine because the brain is like safely stored in that sense. Let's say in a Swiss mountain, it's protected, there's security, and it's actually not aging. And if you combine these two work streams, you basically have a brain that cannot die. Or let's say it's actually a big disclaimer, it can still die due to contamination or virus, or even if it's inside a Swiss mountain, very safely protected. it might still be able to be destroyed if somebody really tries to. So it's like still possible to die, but it's very unlikely that you still die. Like a huge amount of increase that you actually will not die anymore. And these are the two terms, and this is what Eightsix Science is working on.
Then I have 10 follow-up questions.
Sure.
Before we dive in, I just want to set the expectations on what point of the technology are we at. On a scale from 1 to 10, where 1 is taking a pill today, which is very feasible, to 10, which is an interstellar kind of movie, where are we currently at, both in terms of knowledge that this could work on paper and implementation? Because on one of your paper, you write that this could be feasible in even 20 years,
Yes.
which is, let's say, from a skeptical point of view, it is very optimistic because we had been trying to solve cancer for the last 80 years.
Yes.
So what's your stance on the timeline and feasibility and the sci-fi side of things?
So we know that from a pure like basic assumptions point of view, we can actually pull this off. It's more about like allocating resources and talent to do it actually, and also to validate and improve. But from a first principles point of view, it should be possible to maintain a brain alive outside of the original biological body. There are some science questions left, but they're minor ones. And actually, the technology is pretty much here for sustaining an organ outside of the human body. It's just that people usually don't do it for the brain due to ethical reasons, or they don't really have like a very aligned framework with what they want to achieve in the long term. But it's pretty much a bioengineering or like a biotech, neurotech engineering challenge. The brain replacement part has some deep scientific questions left. We know of some mechanisms that seem to work quite reliably. If you ask some brain, like other brain replacement people, they usually always put it onto the one of the big foundational principles, which is cortical reorganization, for example. They say if you have a slowly growing lesion in the brain, that memory actually shifts around. And that's actually an insight into substrate independence in that sense, that information of what you are, so these engrams, what I mentioned earlier, can shift from substrate A, which is the original location of the brain, to a new location of the brain. So if you can do that, the next question is, okay, now you can add a new piece of brain next to it and it would move into that one, right? So like basically they claim substrate independence. And it's true, clinical cases, like even old ones, even in old patients, it seems to work. Like entire speech areas or motor areas in the brains were gone due to like a tumor, like slowly, or like a glioma, like a low-grade glioma. But they were still able to speak, they were still able to move around, and they had no behavioral impact, no introspective reasoning or no introspective way to say that something is wrong. So it seems like the brain is way more plastic than we think it is if it's forced into it. That's what the brain replacement people are saying. But the problem is what I call now in the meantime the grandma's face problem is, what about the like less functional and less retrieved engrams in your brain, such as the face of your grandmother? So if you speak and move your body around, you use it every time, every day. So it seems like if these areas get slowly replaced and killed in that sense, the information seems to transfer or shift around near perfectly. But what about the engrams, so the memories, the encoded information that you retrieve less, like the face of your grandma? Maybe you think about the face of your grandma once a week, once a month, even less. Let's say it's stored in one location and you slowly kill that part over months and years. And then at a future point, you would try to retrieve it, but it's actually not there anymore. You're not even aware of the memories you lost because you weren't aware of them in the first place, that you still had these memories. So that's actually a very deep, like fundamental question that we try to answer at this point. And nobody really has an answer to that. So the brain replacement part is more science. The brain explantation part is more engineering. But at least what I usually say in the company, brain explantation first is a nice strategy because it's a better alternative to cryopreservation. So imagine you actually can take a brain out, you keep it alive, you might put it into an induced coma and try to stretch somebody's lifespan for 30 to 40 more years outside of the human body. And then when the technology is there in 40 years, let's say the brain replacement technology, if it might take that long, I don't think it does, but if it might take that long, it would be there in the future. So it's like a different delayed approach like cryopreservation without all the problems that cryopreservation usually brings in with like continuity and stream of consciousness and stuff like that.
Do you have speculations on, so let's say that we do that. So I put my brain into somewhere else for 40 years, and I'll be happy to do it, let's say, on paper, if I can survive a little bit longer. How will that feel from the first person point of view? Because I wouldn't have my body, and I'm aware that this is pure philosophical speculation, I guess. Would I be feeling it as if I was in a dream, like in some sort of semi-conscious thing, or would I be fully conscious but simply as if my limbs were not there, because they are indeed not there?
Yes. I mean, it depends. When, let's say we don't have the full sensory, like the full bandwidth sensory BCIs ready yet. So you indeed might do an induced coma brain and wait for the technology to be there. So you're just in a coma. You're totally unconscious in that regard. If the technology is there in the future and you have like a full bandwidth sensory interface, for example, into a virtual world or a robot or whatever, or even a new biological body, you just wake up and everything is the same except it's a new body, most likely. However, if you stay like in the whole thing that we're discussing is like called brain vatism, right? It's like brains in vats. How does that feel? What's the embodiment like? Well, how does agency work? If you stay conscious while being in a brain in a brain in the vat, that's very weird, because indeed you don't have like any sensation of anything other than your internal world, right? So that might actually be quite shocking to people. It's actually one of the, I mentioned earlier, the brain explantation is primarily an engineering challenge, but there are some open science questions. And actually one of the open science questions is about what about the shock status, or even the neural shock status, when you have a brain in a vat and it stays awake or you wake it up again without having any sense of agency or embodiment. It might just be you die, actually. That's one
What do you
problem.
mean with that?
Like in a sense of you get maybe in such a weird shock status that the brain just shuts down, because the brain was never meant to be just fully explanted and dislocated from the biological body. However, me personally, I think that's probably not the case. Best case would be it feels like a dream indeed. I don't know if you know this, there's this experiment or effect. I'm not 100% sure. It's called like the Ganzfeld experiment. It's when you try to sensory deprive your brain, which is like a thing you can do yourself even right now. If you want to do it, you can read it up. It's basically your brain starts to fill in sensory sensation from the outside world if it does not receive anything anymore. It's like basically, like people that go floating in like these chambers in salt water and like body temperature, and they don't have any sensory input, no sound, no smell, no feeling. They basically just float around in perfect body temperature. Most people actually start hallucinating, and that's the Ganzfeld effect. So it might be, if you're a brain in a vat, you will just get lots of hallucinations that your brain tries to make sense of the information it still tries to receive, or it still might receive from internal states, which might be in a brain in a vat scenario, just random noise. But this is all speculation, and these are one of the science questions we try to answer. This is all related to sensory deprivation studies, like what happens to a brain if you slowly deprive it of sensory information over a long time of a long period of time, and then try to bring it back, actually, right?
How do you answer this science question? Because it's very easy to understand conceptually how to experiment if the brain is alive, whether you put it out. That's like a very yes or no answer. But these sort of science questions where there is a lot of consciousness involved and personal experience, how do you test it?
Yes, it's not so trivial, actually, because brain explantation, as well as brain replacement, brain explantation more heavily, is a pretty strong slippery slope at some point with consciousness research. Because As soon, for example, you take a brain out, it's like physiologically still alive. You have no clue if it's conscious or if there's like anyone still left. And then you're like in pure neurocorrelate of consciousness research. And then you're like in the basically one step away from the hard problem, or like trying to answer the hard problem of consciousness. So it's actually not that easy to do research in that, because you end up you try not to get into the hard problem question of consciousness straight ahead. You try to get around it. So in our case, for example, it would be a progressive approach to having explanted or partially explanted brain in animal models, and try to do perturbations or probing with whatever we can get that we can map onto a animal brain while it's still inside the original biological body. And then we slowly, for example, deprive it or slowly extract it while still keeping the parameters alike. So we can like somewhat guess and somewhat try to approach what it is like to be a brain in a vat outside of the biological body. But we have some ideas, but it's all very early. But I'm pretty certain we will have an answer to most of these questions by the end of this year.
Let's talk about memories, because before, while you were explaining, let's say, the mechanism of the biohybrid brain replacement, you talked a lot about memories, like maybe the memory shifts from one side to the other, and then you can just replace the part of the brain where the memory does not reside. Mm-hmm. And I have some questions on that, but I guess that the brain is not only about memories. Like, what about, I don't know, the perception of feeling, and let's take fears, no? Which is, I guess, produced by the amygdala. And that's like a very inherent human experience on the good and on the bad. How do those things work in your framework?
Yes. I mean, I don't know in that regard. I have a very engineering first stance on the whole thing in brain replacement. The reason is not that I'm not interested. It's just that from a pragmatic point of view, it does not make sense in a productive environment to ask too many hard problem of consciousness or qualia questions at this point. I am very interested in these questions. That's also the reason why I started a research non-profit organization next to Eightsix Science that tries to answer these questions. It's very complicated, very theoretical at this point. But when it comes to Eightsix Science, it needs to stay pragmatic. The reason there is we know biological brains work. They work for qualia. They work to have like perfect phenomenology. And we have clinical insights that seem to work to shift memories around, whatever memories are. We don't know what memories are. We don't know how actually qualia like starts to exist or be processed on the brain. We don't know. There's some good frameworks actually, but we don't know. We just know that we can brute force these mechanisms in order to achieve a productive goal, which is in the case of Eightsix Science, to solve death. So that's like the frame. Like to give you like an analogy that I try to give people is, for example, physics. If you would have like a bunch of physicists in the neuroscience field, and you try to compare how they build ontologies of the field, it's actually quite weird that neuroscientists and consciousness researchers try to answer immediately always the hard problems, which, for example, a physicist wouldn't do. Like if you ask, for example, what is qualia in this, or like what's the feeling of redness of the red I'm perceiving, like the hard problem of consciousness. It's actually the same question as if a physicist would ask, why does a electron exist? It's like the most fundamental question, like the last why you can actually ask. And even physicists, they try to have some sort of operational way of thinking about their science by creating, for example, mechanistic frameworks to do something useful with it, such as quantum mechanics. Like they don't know what a quark is. They don't know. And we'll most likely never figure out. They don't know what an electron is. We'll most likely never figure it out. But we know what kind of behavior it has and how we can work with it in order to create models to either predict something or do engineering with it after all, right? And I actually have the same view on the brain and consciousness by saying most likely we'll probably never figure out the hard question, because it's the same question like asking why does stuff exist rather than not exist in physics, for example, like very fundamental physics. But we can actually create frameworks to productively work with it. And this is what I'm like trying to formulate. I like somewhat call like operational consciousness mechanics or something like that, like OCM or whatever. It's like a way to work with consciousness and the hard problem without trying to answer it, because it's basically what physicists are doing in the most fundamental physics, in quantum physics.
I see what you mean, but I don't feel that I get it fully in a way that, yes, of course, there are some things which are very hard questions, core stuff, like what is consciousness and where does it derive from? And I fully see why you wouldn't properly have that as a, let's say, operational productivity thing, but just as a backdrop in there to be taken care of later on.
No.
But in the example that I made, like I don't see fears just as an example of an emotion as a hard question. I see it more as a fundamental mechanical thing of the brain. Especially, yeah, I guess that I don't see it as a, let's say, philosophical thing, but more as a mechanistic thing. You know? So it's like hormones being released and everything. And so I was just curious if you see that, let's say, let's call it releasing hormones in the brain. Do you see that as something to be solved 20 years from now and just like, let's just focus on memory? Or how do you properly see this sort of thing?
Yes. The goal that, or like, let's say the assumption a brain replacement has is basically that you create a piece of brain in vitro, so in the laboratory, that somewhat approximates the original tissue you either excised, removed, or you try to squeeze in. And you hope that the host brain takes over and does the rest. So if you, for example, try to give it a percentage, currently, if you take a piece of brain out that like stores memory, it processes like feelings, it like releases neurotransmitters and all that kind of stuff. If you take it out, it has like a percentage of 100%. It's perfect. It was like meant to be there and meant to be part of your brain. Now we try to replicate it in the lab with a biological graft, we engineer in the laboratory. It's most likely going to be an approximate of like, let's say 40%. Then we insert it into that original spot, and we try that the host brain actually takes it in and lets it integrate, like, by letting it grow in and grow into the host brain, and the host brain growing into the inserted graft, that the percentage goes up to 100%. So it's like 100% perfect brain again that can receive and store new memories and do the same thing that the original piece of brain did that you removed initially. It's a lot of assumptions, and actually, if you go deep into the theory of gradual brain replacement, or progressive brain replacement, as it was initially called, there's different approaches. What our approach is like the whole tissue block replacement. There's people saying like maybe you just need to insert a bunch of, for example, progenitor cells, so slow, like pre-differentiated, like induced pluripotent stem cells, and you do that a lot, like you plaster it around the whole brain. Our approach is saying, well, we most likely need an entire tissue block. It needs to have a certain size because we need to have a surgical implantation. And there's also people saying like maybe you don't even need to remove tissue. The whole approach of like you try to shift memories around and then remove that silenced part, as like originally conceptualized by Professor Jean Hubert, who was the person that conceptualized progressive brain replacement. You might not even need to remove it. That's actually also one of our research questions we try to answer this year is, can you do gradual brain replacement by just adding new brain and without removing old brain? I complicated my answer a little bit here, but basically what I want to say is what we insert is somewhat a perfect brain. It will end up going up to 100% to be a perfect brain. And if you have a perfect brain, it will do the same thing that you can do already right now, which is store memory, relive, have qualia, have hormonal release, neurotransmitters, neuromodulators, and so on. So there's actually no need to really answer that question because we stay within biology and normal neuroscience.
It makes sense. You're basically operating at a higher level of abstraction. So you just move the object instead of moving the protons in
Yes.
it.
Yes, exactly.
I guess that this reminds me, what's that guy? It's like top researcher. He used to work a lot with nanobiological robots, and maybe his name is like Michael something. It's like a very big guy in synthetic biology.
Michael Levin?
Yeah, Michael Levin. He was telling something like that in his research as well. He was like, there is no reason for you to move a dog molecule by molecule. You just tell the dog to move, and the dog will move.
Yeah.
And because in his research, he basically, I'm not sure if this is like fully demonstrated or not, but there is some sort of inherent intelligence to biological tissues, and they just know how to do it, even without hard-coded instructions.
Yeah. I mean, the idea of like bioelectricity is, I think, how they call it. Like, I'm not an expert in that. I actually have a good friend who works in his lab, but I don't know everything about Michael Levin's view or like views. But I know about the basic principle of bioelectricity, and it's true that you have like this intrinsic memory that is actually not stored in genes and not stored in neurons or like the embeddings on top of neurons. Which is interesting. And actually, in the case of gradual brain replacement, does not matter. It actually would help even more that you have like this intrinsic knowledge how cells or whole tissues need to behave, or for example, differentiate or achieve a certain cell fate, which is actually what I think most likely the case that we need either way to make gradual brain replacement work. Because the whole assumption of that the host brain can take in a new piece of brain, like it takes them in, it sees how the genetic code is basically the same because it's, well, iPSCs that you derive from your own stem cells or somatic cells. So there's no rejection. Actually, the whole point that it might work most likely lies somewhere in the work Mike Levin is doing with bioelectricity, I think, intuitively. But I don't really have the proper literature overview view on that.
Mm-hmm. Do we have already such a thing of like if I cut a piece of my brain out and put a piece of yours, assuming no rejection, do we have proof already that it works? Like I integrate it and it just works very nicely?
Yes, define nicely because that one is a hard one. But yes, we do, but only in animals. So mostly small rodents, rats, mice. There were some some people that tried like in larger brains, like macaque and pigs. And we're also doing it in larger animals as we speak at Eightsix Science. But we know it works. But the question is like the nicely part. That one is hard to define because that goes really into the fidelity of the brain tissue you put in. Because the problem is if you work with small brains, you don't really engineer in a high fidelity of the new brain tissue you put in. So it's like most likely just a 3-layered or a few layered, somewhat cortical cytoarchitecture, but it's the best you can do. You cannot really like replicate in a high scale, in a high resolution yet. But that's exactly what we're trying to do at the Eightsix Science in the Biohybrid brain replacement effort.
But are you starting purely, let's call it extra piece that you put in your brain, extra piece?
Yes.
Like, do you do it starting from pure biological stuff, or is it still, let's say, wetware, or let's say not purely biological?
Yes, we start from biology because the questions to answer are already hard enough to bring in some unnatural things from day one. But we will quite soon also already integrate the synthetic pieces, like for example small electrodes, into these crafts. Again, not only because we want to have a ultra high bandwidth BCI at the same time without rejection, without clear scarring, and that stuff that you usually have if you have penetrating electrodes, for example, such in a case like Neuralink, for example, but also because we might need it actually, right, for the integration. If you have a piece of brain with electrodes in it, you surgically implant it into the host brain and you stimulate it just with electricity over like a long time, it actually grows into the host brain way better than in the case where you don't do it. So by doing that, we actually already start our biohybrid efforts quite soon, but it's not a priority as of now. We want to stay in normal biology first and then go into the biohybrid approaches later.
What does the brain think when you put such a thing in your head, like a new piece of it? Like, does it just test if it's safe and then it just starts to colonize it? And when it colonizes it, how long does it take? Is it like a 1-year thing? And how does it decide whether that part of the brain will do X or Y in terms of brain function?
Yes, good questions. These are exactly one of the, or some of the very fundamental questions that need to be answered in order to make brain replacement work. Or actually, to give you maybe a better or more pragmatic point of view, we might not need to know exactly how it works before making it work, which is actually my hope, again, from a very pragmatic neuroengineering perspective. Like, you don't need to know what quarks are in order to build airplanes. Right? So you need like a higher abstracted model like aerodynamics, and you can make something work like an artificial like wing or like jet engine and stuff like that. And the hope is something similar. I actually hope we can show it works and what works without really needing to answer the whys or the theoretic foundations in order to achieve our end goal, which is again solving death. So to answer your question, like what does the brain think? I don't know. we don't know. Maybe we might never know, but I think we will most likely know at some point doing fundamental research. But I hope that we can make it work first. That's the goal. So I don't know to answer your questions.
But I'm sort of relieved that, I guess, with this approach, which is not really just like an approach, it just might be the thing, it just might be how it works. But like the perception that I have by talking with you is that, of course, it's such a like a very complex challenge and probably one of the biggest challenges that we will ever had. But maybe we might be lucky enough not to have to go so into the details of it. Because, I don't know, whenever I read about creating digital twin or brain simulation,
Yeah.
I think a lot in terms of having to deal with billions of parameters, but it might not be necessary.
Mm-hmm. Yeah, the thing I'm just looking up, like I think the correct term is I think it's non-organicism. I think. Correct me. It might be wrong, that term, but it's the assumption by saying you do not need to understand the entirety of an organ in that sense or an organism in order to work with it, and that's basically what medicine, for example, is doing. If you're a doctor, you do not need to answer the most fundamental questions about everything in the human body in order to achieve a productive goal, which is, in the doctor's case, to bring a patient or a person or organism back to its original state, which is a healthy state, right? So this is basically the view that I have on these things. And you brought up a very interesting point, which, for example, the whole mind uploading brain emulation simulation perspective. Originally, I was actually a hardcore mind uploader. I was like, okay, that's my life's mission. It was like over 10 years ago when it made it my life's mission. And it has the same end goal. It's basically solve death through engineering means. Death is an engineering challenge. That's basically the same slogan, you can call it, in the mind uploading space. But the problem I had with mind uploading over these questions, next to a lot of other problems, was exactly one of the problem with the approach itself, which is in mind uploading, they need to know a lot more fundamentals in order to make it work, and they still do what we all call like the scale separability. They at some point still make a cut and say like, okay, from that point on we need to understand everything, but below that, not really. In the case, for example, most mind uploaders or people that actually work in whole brain emulation, they do it, for example, from the neuron level on. They say biochemistry, or maybe some actually even above. They say like just from a neuron level, point neuron level on is enough abstraction. Everything below is just implementation details in reality that we do not care about to simulate a brain. But the problem is, that's pretty much the problem we're talking about. In the case of gradual brain replacement, we try to achieve the same goal in solving death through engineering means from a very healthy middle ground by understanding a lot about the brain, but not needing to do a bottom-up approach from the most fundamental things. To give you an example, it's very abstract, but to give you an example, if you want to do mind uploading properly, you would actually need to answer what reality is first, and then you can start simulate a brain. Because For example, people working on quantum consciousness have strong arguments, like saying that it actually needs quantum effects, the collapse of the wave function. I'm not an expert, but they have strong arguments why it needs that. And let's say that's true, then you would need to simulate the quantum system on either a quantum computer or on a computer like a supercomputer. So the scale separation actually is now even further down because you need to do even quantum effects, right? And that's actually such a problematic approach to trying to solve death if you need to get all your fundamentals, all your really, really first principles right before getting into the actual goal, which is solving death by keeping the brain running for as long as possible. In our case, we have this like approach, as I said, I need to look it up again, like this non-organic first view, right? That you say like, well, we know it to a certain degree, what works, what not, and we can work in on this layer. And we don't need to answer all the fundamental questions like what's qualia, what's actually memory, how do memory shifts work. We can show they work without needing to answer them in order to then achieve a productive goal. And this is what actually drove me out of whole brain emulation and mind uploading, because I realized it's a dead end and you will actually end up nowhere in that space. You will be lost in complexity and philosophical questions. And this is what I didn't want because I have the urgency of 19 years left to solve death, right?
Yeah, super clear. I really want to ask you about your journey and how you went into different approaches before landing on this one. But before we do that, I still have like a technical question on, let's say, interacting with the brain, which is when I was reading your paper on synchronetics, I just have this image of hard material inside my head that is going rot because I don't know, it's just like my image that I have in my head. And I don't even know if that's real. Like, do we have materials that can last a good 20, 30, 40 years inside the brain? Is it even a topic in the first place? Like maybe you create artificial neurons and it's not a thing, like they just can self-regenerate. And can you give a bit of an explanation and background on this?
Yes, we do have work on this, but lots of it's like very early and about to be protected, of course. But yes, there are materials, there's ways to have a biohybrid brain that stays biohybrid for at least a few decades. That for sure. The other question is, what's the survival of this material over time? That's still one of the really hard questions because in order to prove that that works, you actually need to do it and let it live in a brain for many decades. The whole field of BCI, like in the classical BCI, to have penetrating electrodes, for example, in the case of the Utah array, is a very rigid, very like spiky, like hard material that you put on top of like penetrate into the cortex basically of humans. Only now we actually have lots of long-term insights into what actually happens to the brain when it has a foreign body penetrated into it. Only now, after many, many years. So these are still some questions we will answer in the long term after doing lots of experiments. And this is again why I think gradual brain replacement with biohybrids especially is more of a science question at this point rather than brain explantation, which is more engineering. So this is a really, really, really good question that we don't know as of today.
All right, let's go through your journey, man. Because you started with a degree in web development, that was your bachelor, and I know you're doing everything that you just explained. What happened? I think that you did also like a couple of masters. You have just graduated, I guess, like 9 months ago, 12 months ago from King's College in applied neurosciences. Please give us a bit of more details on what happened in the middle steps.
Sure. I mean, technically, I would like to give more context in Switzerland. I grew up in Switzerland. In Switzerland, you have like these apprenticeships. So after high school, you either decide to do an apprenticeship, which is pretty much an education mixed with a job or like an internship slash apprenticeship slash job, right? And you still go to school, or you go to full-time school to prepare for your bachelor's. And there's this usually the same length. I went for the apprenticeship path. Why? Because my original goal in life, let's call it like that, was to just go into design design and actually the creative fields, like maybe even creative technology to a certain degree. That's it. But after like let's say like pretty depressive phase in my life, I started questioning actually everything. Like, is that what I want? Is this where I see my future in? And is this what I want to leave to this world before I die, basically, right? So that's what you should call like your immortality project, because everyone knows about that they're dying at some point today. Start asking, what's the thing I leave behind? Is it either I bring the values to my kids? Is it I build a huge company? Is it I create or like discover a new thing and I will be remembered for infinity, which is not true, in the rest of humanity, right? Your like immortality project. So I started questioning that myself at age 17 or something like that. And after many months, I ended up on Neurotech. I said like, that's actually very interesting. And with a more focused point after time, mind uploading. Why Neurotech first? Because I started realizing neurotechnology is interesting because for the first time in humanity, we start engineering something that is not external to us, but ourselves. Like usually when we invented the car, trains, smartphones, whatever, it's always something external to us. But now we can start engineering brains, like manipulating brains, create BCIs and stuff like that. So the first time that we engineer ourselves, which is cool, and I thought that's pretty cool. But this later drove me more into this view, what I called the essay about, which is death is an engineering challenge. Like the whole reason why one actually does or thinks about their immortality project is because one knows that you will die. But let's say you start questioning that question, do I need to die or is there actually a way around it? And it seemed like back like 10 years ago, I thought, with my limited understanding back then, it seems like dying itself is an engineering challenge. We can maybe get around it for the first time ever since life exists on planet Earth, right? And that really motivated me. I was like, okay, let's try it. So this is now my life's mission. Basically, let's try solving death or die either way, right? So that's my motivation in life now. And this back then drove me to quit my apprenticeship, start studying, get a new job. And why, for example, web development? Back then I was what you call like an interactive media designer. So it's like a designer doing like user interfaces, UX design and stuff like that, very closely to the technical field. And I knew if I want to get into mind uploading, I need to become very technical, very fast. And doing web development was actually the most logical step to progress into a technical field based on my existing skills. So that's the reason why.
Would you have gone through the same route if you could go back today?
In today's world, like 2026, probably not. Don't do the same path. Back then, maybe if you're in a similar position. But also must say, if I would be able to take a lot of, like, or let's say a small bit of my knowledge back to 10 years ago, and I would try to think about it again, like what's my path to get towards that goal, I would probably do it slightly differently. I would, for example, try everything to get into, for example, physics first, or mathematics first. That's like something I would probably change. Like go into the hard fields, do the hard thing first, and then go out to whatever you want to do afterwards. But again, this is like the like you try to be smart afterwards after you know what has happened. Most likely, I wouldn't change anything as it happened because I'm quite happy with everything as it happened the past 10 years. So I wouldn't change anything. It's perfect.
I would love to go even more into the details. Like, so you're there, you've done web development for a couple of years, and then you're like, okay, now I'm ready to go even deeper. What happens inside your brain? Like, why did you decide to go to King's College? Were there any other options, like career path wise? Like, I really want to understand what happened in your 20 years, 24 years old Daniel version.
Yes. I mean, that's the thing. If you have a very clear vision, you can make very quick decisions in your life. So, meaning you can switch between being tactical and strategic quite a lot because your vision is quite rigid, but your implementation details are quite, ambiguous, which is good. So, for example, my original plan was, okay, I will work now, make some money so I can finance my bachelor studies. I always worked full time during my studies because I wasn't wealthy. I didn't have rich parents or anything, so I need to pay it for myself. So I always thought like, okay, after the bachelor's or during the bachelor's, I want to get like into something neurotech related, and then afterwards do a master's degree, maybe as an intermediate step, do a second master's degree, because doing a jump from web development into, for example, neuroscience is quite rough if you don't do maybe something in between. So I had like a certain way of how to do like what I usually call like this semantic transition from the field I am right now to where I want to go. And where is the field I want to go, which is basically simulation neuroscience. So what do you need to do in order to do simulation neuroscience is you need to know neuroscience and you need to do software engineering. You need to be quite strong with programming and doing maybe some physics simulations and stuff like that. So I had like a pretty clear progression, like some masters inside, I wanted to do a PhD initially, and like a very clear path to end up where I wanted to end up, which back then was actually I wanted to work at the Blue Brain project in Switzerland, which is probably the closest you can do as a normal employee to work on mind uploading. Like just to maybe for everyone listening, the Blue Brain project was like this big initiative where they tried to simulate the entire mouse brain on a supercomputer. And ultimately, they wanted to simulate the entire human brain on a supercomputer. And they did that in Switzerland. I was in Switzerland. So it seems like a very logical way to work there and see what happens afterwards. But over these years, that's what I meant with you have a clear vision, you want to solve death. It doesn't matter what exactly you do in order to do it. Initially, it seemed to be mind uploading, like scan, store, simulate in a supercomputer. Over time, it became the thing what I'm doing right now at Eightsix Science, because I realized, well, as we discussed earlier, all these problems. So if you have a clear vision, you can make quick decisions in your life and be quite tactical. For example, I saw there's a neurotech company in Switzerland, early one, and they're hiring web developers. So it was like an obvious step. Okay, let's do it. Let's scrape my plans and let's be very tactical and get into that company, because then I'm finally in the neurotechnology field. If you're in that field, you might be able to do like shortcuts. For example, I always thought I might need to do a master's in between doing a neuroscience master's to really get the knowledge from neuroscience. But by working in a neurotechnology startup, I was able to actually straight after my bachelor's do a master's degree in neuroscience, because I could convince the people there that I had good enough knowledge in neuroscience due to me working in the neurotechnology field already for over a year. Right? So this is like what I meant. You need to be very, very clear on your vision, which helps you making very quick decisions. And by that, you can play tactical or go back to being strategical again, which is quite good in life and companies and even playing chess. I love playing chess. All these analogies come from chess, basically. So it's quite useful to have a clear vision and stick to it for as long as possible.
When did you decide to properly launch a company? And how did you get to Draper? Which, by the way, I was kind of surprised, because I think that the general stereotype amongst people who work in longevity is that people, especially institutional investors, try to separate themselves as much as possible, at least publicly, from this sort of very, I don't know, controversial science, if you're, let's say, outside of the bubble. But here we go, and you've actually raised from them. So was it like an exception that you got the money from such a fund? How was your journey into that?
Yes, it's a good question, because initially I wanted to become a professor and just create a lab, because I was always convinced the past 10 years that you cannot create a company out of what I'm trying to build, which is somewhat true, and I still hold a somewhat similar opinion to this day. But I figured out around like late 2023 that doing non-classical mind uploading, so doing like what I call now hybrid mind uploading in the meantime, which is what we're doing at Eightsix Science, for example, after all. If you do that, you have a clear commercialization pathway. So for example, if we create small brain pieces in the lab that have like a very high resolution, or they're like very patient specific, and they're biohybrid, there's actually a lot of people that would pay for that for several reasons, to do research, to do like drug development and so on. By having this realization, I actually was like, oh, actually you might still be able to pull off a company out of the first steps while getting towards the end vision, which would be very hard to commercialize from day one, right? And this is actually what I think is the problem with mind uploading companies, for example. They say, please give us like $1 billion, and and we're going to simulate a human brain on a computer. And then we achieved it. But until then, they have like this death valley of they can't really do anything that's useful to a lot of people outside of the field of mind uploading and whole brain emulation. So this was like one of the realizations I had like 2023, somewhere around that time. I was like, okay, let's try to create a company. And how I came to Draper is random coincidences, as life wants it, as always. I mean, I used to work with a friend at one of the startups, actually the Neurotechnology startup I mentioned before. We used to work in a company together, and we became good friends. And his brother is a VC in London, not in US, but in London. And his brother knew the son of Tim Draper, and then things happened. And actually, the son of Tim Draper, Adam Draper, at Boost VC, which is an amazing VC firm, they were my first check in 2024, in summer 2024. And then I was actually able to quit my jobs and just work on my company full time. And after a while, by showing amazing progress, we were lucky that we actually showed amazing progress quite early on. We were able to convince a lot of VCs, including the father of Adam Draper, which is Tim Draper at Draper Associates as well. And then things happen. It's not straightforward like that. We just said like, can you ask your father? It was actually more complicated than that because they did actually some pitch competitions, and we got into that, and they weren't aware of us. So it was quite complicated and quite a journey, but we were able to pull it off after all. And just to maybe give a last context on what you said before, it's not true. Tim Draper is actually, yes, very institutional-ish, classical VC, but not really. I mean, he came from a background from investing in SpaceX and Tesla, which was back in the day quite ridiculous, or even like Coinbase, right? Together with his son, that was actually one of the early big investments together with his son, as far as I know. So it's not true. Yes, there's a standard VC firm. They need to make returns with like more safe like investments, but they do a lot of crazy stuff actually. I know of a lot of crazy stuff that they're investing in, which I'm probably not able to share, but they do a lot of crazy stuff that they that they're interested in, and also talk about risk taking. Also not true. I mean, the most famous example that didn't work out with Tim Draper was Theranos with Elizabeth Holmes. I mean, that was like probably the most famous example of something that just did not work out and actually was quite a controversy, right?
Yeah.
So it's not true. I think he's quite a risk taker, which I admire. I think it needs more people like that in the VC world that just like do the big bucks into high risk, high return endeavors like Eightsix Science.
Well, amazing story. I had never thought about the, let's say, the middle steps strategy revenue wise that you just described, because all of the biotech projects they always follow like the same pitch revenue wise, like it's like the value of death, and maybe we get FDA approval in 20 years and then maybe we make money. But in your case, it is actually remarkable that, and correct me if I'm wrong, maybe you can actually create a bit of revenues already in a couple of years, because you would be selling tools and pieces to other labs. So it's not that you're selling stuff to humans. Like you can generate revenues as soon as technically feasible, which is insanely good.
Yes, exactly. Yes, like I usually give people the analogy of SpaceX is they have like this moonshot, and in their case, Mars shot goal of going to Mars and colonize Mars, which takes hundreds or even thousands of years to technically pull it off to bring it up to 100%, and it takes decades and billions of dollars to pull that off. So how do you pitch that to investors? You're not saying like, well, we're gonna go to Mars and that's it. Please give us money, right? That would be like you have the Death Valley approach and you're stupid in that regard. No, you say like, well, we start with creating reusable rockets. That's our one main differentiator in our way to go to Mars. And that's the approach, because when you, for example, create reusable rockets, you can already commercialize that quite early on. And you can go the step next, which is, okay, we have reusable rockets. We can reduce the price of kilogram per, like the payload kilogram cost. Now you can do stuff like Starlink. And now Starlink is actually the cash cow of SpaceX. It's probably going to finance the entirety of the Mars missions. Just SpaceX, relying on Starlink, which is kind of crazy. And this is usually the pitch I give to people, is saying like, well, we know we have a bunch of potential Starlinks on the way to the end goal that we can start commercializing. There's probably some unknowns as well that we weren't like aware of. I'm also unsure if, for example, Elon Musk was aware of that Starlink might be a thing when he started SpaceX. Most likely not. So there might be some things like that as well that are ultimately cash cows for our business. And this is basically the bet that we're doing. We're not saying like, please give us money. We're classical med tech, deep tech. Thank you for the cash. We see you in 10 years when we hopefully figure it out. No, we actually have quite a lot of progressive milestones that we can commercialize on. And we can even try. You can even do like A/B testing on your product and see, okay, let's try that. And we figure out, that doesn't work that well, or it's not really that much of a sustainable business. Let's try the next thing. But you already have shown your investors quite early on that you're caring about these things, that you try to commercialize and actually make a business out of it. And that's true, as you mentioned, like we are actually trying to get our first paying customer this year, which is kind of wild because we have like this very long 20 years time horizon as well. But we try to get a paying customer in the second year after incorporating the company, which is actually absolutely bonkers for a deep tech, med tech company. But I think it's possible if you do it in a very intelligent way. So let's see. Ask me in a year again if we pull it off, but I'm pretty confident that we can pull it off.
Will do. As a last thing, can you actually disclose examples, theoretical examples of these Starlinks, or is that like secretive?
No, not at this stage.
Okay. Then actually, as a last question, and I wanted to ask you, because this is more of a logistical question. So I see that you're partnering up with a Japanese university and a Japanese professor. Is that like a must in your company journey, or is that like if a company wants to build something adjacent to what you need to build, like is a partnership with a university crucial, or can you also do it without it?
Most likely you can do it without it, but the circumstances need to be different. Like, for example, what I did in fundraising was to do vision first fundraising, which gives you freedom to operate if you pull that off. So like I went to fundraise, for example, to Tim Draper, saying second slide deck, solve death. We want to try to solve death with engineering means because death is an engineering challenge. And then we basically went from that vision back to what we're doing right now, which is vision first fundraising, which is kind of crazy. Usually you cannot pull that off as a especially first time founder, early career person, because it's quite bonkers, because people will just look at you and say like, you're crazy, forget it, do something easier, maybe do that as a second company. It's usually what I heard. And it's true, like 99% of all the VCs I talked to were basically a hard no straight from the beginning. It's like too sci-fi, too deep tech, too weird, too whatever. But I knew that if I was able to pull that off, to, for example, do a pre-seed round with the vision first fundraising strategy, it gives us freedom to operate, which is good, because then it's the same principle. Everyone knows the vision and the implementation details are quite flexible. So you don't need to do what you have pitched, what you're going to do, but they know what you want to achieve, which is quite smart. So to the Japan point of view, if you are somebody like Elon Musk, you might be able to fundraise pre-seed 50 millions, and then you don't need to do academic collaborations with universities from day one, right? But that's a challenge. In my case, I needed to do that because I raised a smaller amount, because it was otherwise impossible to raise any amount for that kind of vision first fundraising. So it's like, as you see, like pretty much a 5D chess game in order to figure out what's possible. So yes, it might be possible, but the circumstances need to be different, that you can do it without it.
Amazing. Daniel, this was incredible. I really wish you to succeed, not only for you, but for the rest of humanity as well.
Thank you.
And yeah, so thanks a lot for coming in, and good luck with everything.
Thank you very much. Thank you for having me.